This is about turning effects of forces. Turning effect of forces. Let me zoom in a bit so that we can see it properly. So, like you said, these are the areas we're going to look at. Your objective is you need to understand the way may be acting or may be taken as acting at a single point known as its center of gravity. Define an moment force. Understand the purpose is that acts to produce rotation only and apply the torque of a force. Okay. Let's start with the center of mass or center of gravity. Do you know what the center of mass is or the center of gravity is? You may need to be audible, please. Yes, you may need to be audible. Okay. Center of gravity. I hope you're on the Jamboard. Please make sure you are concentrating. Center of gravity is the point where the resultant weight of an object appears to act. Did you get that? Let me give you an example. If you have this, I hope you can hear me where you are, young man. Confirm that you can hear me and where you are. I hope you can. Consider this object. Please make sure you're on the Jamboard. Are you? Or perhaps you may just let's look at it on the screen. Boyo, please, you can turn down your laptop. Let's look at it on the screen. It's better so that both of us can concentrate. Can I continue? Now consider this object. It has several particles, all of them with their individual gravitational force. In what direction does gravitational force act? Downwards to the center of the earth. So this is acting downwards. Assuming I'm using this to represent the particles. Imagine there are only how many particles involved here? 1, 2, 3, 4, 5, 6, 7. Just for the sake of explanation, let's say we have only 7 particles, and each of them experiences gravitational force acting downwards to the center of the earth, vertically downwards to the center of the earth. Now, you can find the resultant force. For instance, by the way, what is the resultant force? What is the resultant force? What is resultant force itself? That's what I'm saying. Can you answer me? Anyone? What is resultant force? What does it mean? That's what I'm saying. What is the meaning of resultant force? Resultant force is the effective force of a system of forces. Net force, the net force. For instance, if you have 50 Newton acting downwards, 20 Newton acting downwards, what's the resultant forces? 70 Newton acting downwards. In fact, when they act in the same direction, you add them up. But if they act in different directions, what do? You subtract. So resultant force is the effective force or the net force. First of all, I need to say that the resultant force is the effective force or net force. Okay, let me write it down here. No. The resultant force is the effective force. The resultant force is the effective or net force of a system of forces. Of a system of forces. We talked about that when we're looking at mechanics. In this case, the resultant force for these two forces, 50 Newton and 20 Newton, will be 70 Newton. The resultant force will be 70 Newton because they're acting in the same direction. It will be 50 plus 20, which is 70 Newton. If they're acting in the same direction, you add. If they're acting in different directions, you subtract. Now, so I said, for this that I have here, represented with 1, 2, 3, 4 different particles with their gravitational force, with their weight, how do I calculate their resultant force? Add all of them because they are all acting in the same direction. I will add all of them. If there are billions of particles involved, I will add all the gravitational force of each of those particles. Now, where that resultant force acts is its center of gravity. So, resultant force is net or effective force of a system of forces. So, when we have find the resultant force, in this case by adding. Now, where those resultant forces are, where the resultant force acts, is the center of gravity of that object. Usually, if the object is with a uniform cross section, the resultant force will act at its geometrical center. Let me explain. So, in simple terms, I can use some values. If this is 10 Newton, this is too much. I have to reduce this is 10 Newton, this is 20, this is, for illustration, this is 4, this is 5, this is 2, this is 3 Newton. What's the resultant force of these forces? What's the resultant force of all? That would be 10 plus 10 plus 10. That's
60 plus 40. That's 60. So 60 plus 40 is 100. 100 plus 5, that's 105.
100.
That's now 110.
That's 110. So 110 Newton downwards is the resultant of all this. Now, the point is what we call the center of mass. So this point, I'm going to represent it with marker, is the center of gravity. So let me define it. The center of gravity is point where the result is Can you see that? Where the resultant weight appears at. So it means that if I want to balance it, all these forces together, what can I do to balance this object? This 110, that's the resultant force. What can I do to balance this object? Can you, like, so that it will be in equilibrium? You know, when the forces are balanced, all those added together produces a result. So if you have 110, yes, you have to apply a force of 110 in the opposite. Yes, 110. So you apply a force of 110 to be balanced. So this is what I mean. If I have this force now acting in the gravity, also 110 balance it. Now acting in the opposite direction. This is why we know what the center of gravity is, because it shows us where the resultant weight is. So if we know where the resultant weight is, we can apply the same force in the center. Are you getting that? Please respond if you are getting what I'm saying.
I'm listening, sir.
Good. So in summary, the resultant weight center of, because the center of gravity. So if we can apply an opposite force, as long as through that will be balanced. For instance, overall resultant. Are you sure? Please, let's. Can I hear you from from your end? What's the overall resultant force? I want to hear you from your end, young man.
Resultant force.
Yes. Think about the total force. The blue. So what is the overall resultant force now? Are you thinking? Are you still here, or you're thinking about it? You can see that the overall resultant force is 0. Because when the resultant from. Okay, so let's go to the next page and talk about the principle of equilibrium. Please confirm if you are still with us. We are not hearing you from your end.
I'm still with you, sir.
Why? How come I wasn't hearing you? Now let's look at the principle of equilibrium. For there are two conditions that must be satisfied. Can you read the first one, Boyo? In one direction, go upwards, total forces. Good. Once you hear me, you respond immediately. For an object to be in equilibrium, total forces in one direction must be downwards. That's exactly what happened. This figure I gave you. If you apply, which is one force, you apply 110 Newton upwards, which is exactly equal to the force, and acting in the same axis, which of course gravity. So can we say that again? One condition necessary for equilibrium. Can you read it out again? Let's go.
Total force in
one direction
is equal to total force in opposite direction, which is downwards.
Yes. Total force in one direction, for instance, upwards, must be equal to total force in the opposite direction, like downwards. Or total force in one direction, like, for instance, to the right, must be equal to total force in the opposite direction, for instance, to the left. Now, the next condition is, another way to put, first of all, before I talk about the next condition, another way to that is to say, or resultant. Is that not what it means? If total force in one direction is equal to total force in the opposite direction, it means the resultant force in that direction, isn't it? Okay, let's take the second condition.
Total clockwise movement is equal to total anti-clockwise movement.
Total clockwise moment. Total clockwise moment is equal to total anti-clockwise moment. These conditions must be satisfied for an object to be in equilibrium. Okay, first of all, what is moment? These are things we already know. What's moment? Somebody should define moment for me. What's moment? Define moment. While I'm waiting for you, let me write these things out again. Condition for equilibrium of a beam. Condition necessary for the equilibrium of an object. The first one, are you still with us?
Yes, I'm still with you.
Okay, total forces in one direction is equal to total forces in the opposite direction. And if that is the case, if the resultant force in that direction is 0. In other words, resultant force is 0. Resultant is equal to 0. Or resultant force in any given must be 0. That force is okay, the first condition, I'm going to write it in yellow. The second condition, do you remember the second condition? Who can remind me? Do you remember?
The second condition said that total clockwise movement is equal to total anti-clockwise movement.
Good. Total clockwise movement is equal to total anti-clockwise. Beautiful. It was. In other words, you can simply say the resultant moment is equal to 0. Or you say resultant moment equal to 0. That's this now. Net moment. Because if total clockwise moment is equal to the anti-clockwise moment, that means the resultant moment has to be 0. So I was trying to ask you to define this first moment. Before we continue, what is moment? Making an attempt. What moment?
Moment is
Yeah, I'm listening. Go ahead. Do you have an idea? Moment is what? Yes, you were saying something. Okay, let me remind you. Moment is product of force and perpendicular distance from the pivot. Only force times perpendicular distance from the pivot. You know, product means times, isn't it? So moment is force times perpendicular distance from the pivot. Let me just write it in simple terms. So moment is force times perpendicular distance. Okay, I think I better write this one down. Times perpendicular distance from pivot. So let's go. Moment is force distance from the pivot. Did you get that?
Yes.
Alright, force and perpendicular distance from the pivot. Very interesting. Let's use this question to illustrate what we mean. I'm on page 2 of 9. I can zoom out a bit to reveal it better. Look at this. Are we ready? Look at this. I'm coming. Let me see. Good. Look at this. The whole of this picture. Boy, are you still with us? Let's make sure you're looking at the screen. This is a uniform meter and it has a mass of 100 grams. I hope you can see the diagram. If you're not seeing it clearly here, you can look at it on the Jamboard. I'm on page 2 of 9. A meter, what's the length? A meter, as the name implies, what's the length? 1 meter, which is 100 centimeters, isn't it? Hello, Boyo. I need you to look at this so that you see where I'm pointing at. I don't want you to miss out on the discussion. The whole length is 100 centimeters from one end to the 100 centimeters. This piece is the center, and there's a force on the 80 centimeters. Right? This is 80 centimeters. Okay, let me use a color that will bring it out better. 80 centimeters. Of course, here is it is the whole length. This point is 25. This point is 25, and the vector is the 0 mark. Okay, I think I need to draw this so that you can capture this better. Just a sketch. All right. So this 200 is acting somewhere. Hold on. Let me put it properly. It's acting at the very end. All right, let's go. We are asked to find F. What do you think we should do, every one of us? What do you think we should do? We need to find the value of F. Are you there? What can we do to find the value? Please. Yeah, I need you to respond if you're listening. What can we do to find the value of F? I think we are even also required to find the value of a force. We'll do that later. So one at a time. Let's start with all the forces that are acting. What's the mass of this ruler, by the way? I'm circling it. Make sure you're looking at the screen so that you can respond immediately. What's the mass of this ruler? This can add what? The mass is after. So if the mass is 100 grams, what's the weight? The mass of the ruler is 100 grams, so what will be its weight? Mass is over the SI unit, kilogram. So 100 grams is in kilogram is what? 1,000, isn't it? That gives you 0. Am I right? So what's the weight? You know weight is times G, which is 0.1, 9.1, and 0.81. Do you know in physics you use 9.81 for your G? In mechanics, and the approximate value 10. But in physics, get your calculator and get me the value of this. 0.1 times 9.81. That should be about 0.98, 0.1 Newton. Please, can you get it? Okay. This gives you 0.81 Newton. Okay? Can you respond at your end?
Yes, sir.
Always make sure you are responding immediately so that we can all carry you along. Can we see the weight is 0.9 Newton because the mass is 100 grams, so 0.981 Newton. Where does the weight of an object act? At its center of gravity. Is that not what we said? Where does the resultant weight act? That's why I started by all of that. If you are looking at the screen or if you see it at your end, can you read what I just circled here? Hello, Boyo. Can you read what I just circled here? The resultant weight of an object appears to act. And like I said, I use the word appears because it may not even be inside the object itself. It's possible that the center of gravity will be outside of the object. So that's why you must, anytime you're defining it, you must include this word appears. It must be in your definition. Because the center of gravity, like in this case, the center of gravity is actually shapes that the center of gravity may not be inside the object, it may be outside of the object. Think of you have a ring like this, a ring that is. Are you getting? You know what I mean by ring? Are you listening? A ring. Where do you think the center of gravity will be? Obviously, it will not be actually on the frame hollow. So the center of gravity may not be exactly where the solid object. It may be somewhere out the solid part of the object. What appears. The center of gravity is the point where the resultant weight appears to act. For an object with a uniform cross-sectional area, the center of gravity is at its geometrical center. I need to say that. Let me zoom it in and write it out properly. Please, can you read what I just wrote, Boyo? Read what I just wrote in blue. For an object with a uniform cross-sectional area, the center of gravity is at its geometrical center. What I mean is, if you have like a ruler with a uniform cross-sectional area, not thicker at one point and thinner at the other point, if it is a uniform cross-sectional area from one end to the other end, or from one face to the other end, the center of gravity will be at its geometry. So look at this object now. Look at the equation we are solving. Alright, I said for an object with a uniform cross-sectional area, the center of gravity is at its geometrical center. Anytime an object has a beginning to the end, Boyo, can I have your attention now? The center of gravity must be at its geometrical center. For instance, this is a meter rule. A meter means. So where do you think will be its center of gravity? This is a meter rule. The geometrical center is at. And I said that is where you have its center of gravity. That's where you have what?
Center of gravity.
And what happens in the center of gravity? Can you go to page 1 and remind us? What happened at the center? I'm sharing my screen so you should see. The center of gravity is where the resultant weight, is where the weight of that object will act. So it is at this that the weight will act. Where are you there? This 50th centimeter mark is weight. So I want to represent the weight here. This is where the weight will act, being its center of gravity, G. And what did we calculate for the weight?
Okay, yes sir.
What did we get for the weight? What's the value we got for the weight? 0.918. 981, yeah. .981 Newton is, and since the geometric gravity will act, so the value of that weight, which is 0.918 Newton, will be represented here. 981 Newton. Okay, we have all the forces. Now let's start solving. What are we asked to find, by the way? Find the value of F and the value of. Shall we go? Everybody listen on.
Yes, sir.
I gave you 2 principles necessary for equilibrium to occur, or 2 conditions for equilibrium. Can you remind me again? Just say them, so I don't have to go to that page. Even though it's still on this page. What are the 2 principles for equilibrium? It's still on the same page that I'm sharing.
Total force in one direction must equal to total force in opposite direction. And total force in clockwise movement must equal to total force in anti-clockwise movement.
No, not this first one is correct. Total force in one direction is equal to total force in the opposite direction. But the second one, clockwise movement.
Okay. Yes, sir.
All right. So you can apply any of those conditions. We get what we're looking for. Let's apply any of these conditions. Total clockwise moment is equal to total anti-clockwise moment. Now, when you are taking a moment, take a moment about a particular, in this case, the pivot, the object rotates about. Remember, moment is force and angular distance from the pivot. So, let's go. Please, I need you to watch what we are doing. Let's go. What's the most 200 Newton force? This distance is 10 centimeters. Why this one is 25 centimeters? What's the moment of this 200 Newton force? Can you stand up, please? What's the moment of this 200 Newton? So what's the moment of this 200 Newton? Do you need to remember what moment is? It's here. Looking at the screen, and I expect that you should be looking at the screen. I am circling it. What is moment? What is moment?
Moment is first and perpendicular distance from the pivot.
Yes, first and regular distance from the pivot. So the question I ask is, what's the moment of this 200 Newton force? Remember, moment is force, perpendicular distance from the pivot. What's the value of the force? Say it.
Value of the force is 200.
What's its distance from the pivot? What's its distance? Try to change to SI unit. Right? 25 centimeters in meters should be 0.25 meters. Okay, so what's the moment of this 200 Newton force? It will be force, which is time. Always measure distance from the pivot. Another thing we need to ask ourselves is, this 200 Newton force, will it produce a clock? Clockwise means it is going to turn it in the direction of the clock, the way a clock. Anti-clockwise is in the opposite direction to the way a clock turns. You are goes right, top, left to right. But anti-clockwise is the opposite way from about it. If it's of 200 Newton, how will it turn this? Will it turn it in the direction of clockwise? Are you thinking?
Yes, sir.
This 200 is going to turn it. This 200, if we pivot. Okay, let's even run through all of that. What will the 50 Newton force? Will it be clockwise or anti-clockwise? The 50 Newton. The 50 Newton force will it be clockwise or anti-clockwise?
Clockwise.
And then you have this thing in the direction of the clock like this, clockwise. Take the anti-clockwise. If we are pinning at the moment, all forces will it F that we're even looking. Are you ready? Let's go. Act. How will F? Will it be clockwise or anti-clockwise? I need you to check this and answer. I didn't hear you. It will act clockwise. How will the resultant act? The resultant will also act clockwise. 50 act anti-clockwise. What about 200 Newton? What about 200 Newton force? Can you 200 Newton? So let's use moment. So I will say taking moment about point P. So I'm going to write taking moment about point about P. Or the total anti-clockwise moment must equal total clockwise moment. So I can write total anti-clockwise moment, total anti-clockwise moment. So let's see all the ones that are anti-clockwise. Remind me again, please. This is where it's important. Let's go. Which ones are anti-clockwise? Because if we take moment about applying the principle of moment, total so what are the forces that are anti-clockwise? 200 Newton is anti-clockwise. So what's its moment? Let's go. Remember the pivot. So force the force. Pivot. Remember you have to use in SI units. That means change the centimeter to meter. So I'm going to write.
Yes.
I'm going to write 200 for the force times 0.25. That is the moment for the 200 Newton. 200 Newton force. And it is anti-clockwise. That's why I'm writing it on the anti-clockwise. The ones in anti-clockwise I will use yellow. The ones in clockwise I will use blue. Clockwise will be in blue. Okay, any other anti-clockwise? We've identified the first anti-clockwise. Any other anti-clockwise? Let's confirm. 50 Newton is done it this way. The weight, so like that's the only anti-clockwise. So let's write all the clockwise equals. Let's write all the clockwise. Which one do you want to start with? Let's start with the 50 Newton force, if you like. 50. Can we go 50 times what? Times what?
So
we needed to also consider the moment of the 50 Newton force, which is this, and the force is 50 Newton. The distance from the pivot is this, from here to here, and this place is 10 centimeter mark, while this position is where the pivot is 25 centimeter mark. That means the distance from here to here will be 15 centimeters. So the moment for the 50 Newton force is 50 times the distance, or 50 times 0.1. So that's 50 times 0.15, actually it's 50 times 0.15. The distance from here to here is 15 centimeters. From the 50 Newton force to the pivot, position of the 50 Newton force to the pivot is 15 centimeters, or 0.15 meters. So the moment is 50 times 0.15. That's for the 50 Newton force. That's another clockwise moment. Then we have another clockwise moment, the 0.981 Newton. The 0.981 Newton, that's the weight which acts as the geometrical center, or the center of gravity, the 50 cm mark. The distance from this 50 cm mark to where the pivot is 25 centimeters, because the pivot is at the 25 centimeter mark, and the center of gravity where the weight acts is 50 centimeters. So the distance from here to here is 50 minus 25, or 25 centimeters. So the moment of this is 0.981 times 0.25 meters. 0.981 times 0.25 meters. Finally, the force that we're looking for, F. The moment is the force times the distance from the pivot. The force is at the 80 centimeter mark, and the pivot is at the 25 centimeter mark. So the distance is 80 minus 25. 80 minus 25, which is 55. 80 minus 25 is 55, and so we're going to have 0.55 times F. That is the force, which is force times distance from pivot. F times this distance, which is 55 centimeter, or 0.55 meters in SI units. So we have this is 0.55 F. The 50 Newton force is, in summary, the 50 Newton force is 50 times 0.15, which is the distance from the pivot, from here to here, 15 centimeter, or 0.15 meters. The weight of the meter rule is 0.981 times the distance from the pivot, which is 0.25 meters, or 25 centimeters, from here to here. And the force that we're looking for is force times its distance, which is 0.55 meters, or 55 centimeters. So we have all here. All of this in blue are clockwise moments. This is the only anti-clockwise. Now when we solve this equation for total anti-clockwise moment equal to total clockwise moment, we can find that F is 76.8 Newton. Now the question also requires us to find R. There's a force on the pivot, R. To get R, we can apply the second condition for equilibrium, which is total forces in one direction is equal to total forces in the opposite direction. In other words, total forces upwards will be equal to total forces downwards. We may not be sure about the direction of the force at the pivot, that's R, but we can assume it to be acting upwards. When we assume it to act upwards, if we get a positive answer, it means what we assumed is correct. The direction we assumed is correct. But if we get a negative answer, it means it is actually acting in the opposite direction. So there's no need to bother ourselves. We can just assume that it is acting upwards. So the force R is acting upwards, assumed. So all the forces acting upwards are 50 Newton, and R while the forces acting downwards are the 200 Newton, the 0.981 Newton, and the F that we just found. So total upward forces 50 and R are the upward forces, 50 and R are the upward forces, will be equal to total downward forces, which are 200, 0.98, and F. So we can state that total upward forces equal to total downward forces. It's always better to write these things out. For lack of space, I have used abbreviations. Total upward forces equal to total downward forces. And the upward forces are 50 and R, as you can see. 50 and R are the upward forces. 50 and R are upward forces. We assume the R to be acting upwards. When we get our answer, we know if what we assume is correct. That will be equal to, that's for the total upward forces, 50 and R in green. The total downward forces are 200, 0.981 and F. 200, 0.981 and F, which is 76.8. So total upward forces equal to total downward forces. That's the equation. We can solve all that to find R. R will be equal to 228 Newton. So we got a positive answer for R. That's positive. That means the direction we assumed, which is upward, is correct. If we had gotten negative, it means R was acting downward. But since we got positive 228 Newton, is acting in that direction assumed, which is upward. So it's actually upwards, as assumed. All right. We could have taken moment about any point to find R, but that would be cumbersome, so there's no need. We could just use total upward. In fact, if we wanted to do that, we could take moment about F to find R. If we take moment at about position F, we can still find R, but that would be cumbersome. It's better to use total upward force equal to total downward forces. Total upward forces equal to total downward forces, and we can easily find R. Okay, there are some other questions we can look at, like this one. Here we are required to find F, which is this force F. Here is 10 meters. This place is 12 meters. The center of gravity is acting at the geometrical center. This force is 200 Newton, this force is 15 Newton. We're looking for F acting in this direction. And the mass is 50 kg. We can see forces acting at different points. This is 100 Newton, this is 150 Newton. This can serve as practice questions. There's another one here. These values are provided. We are required to find P. If we can take moment about this pivot here. Same principle. That's a question. We have another one we can practice, this one. Now, I provided a hint to be able to get this, because initially, this is actually, let me leave it the way it was initially. This is the diagram given. This cable is acting at 30 degrees to the flagpole, and we have the weight provided and different other things. We can calculate the forces taking moment about this position where it is hinged, this point. We can call this point P, where we're going to take moment, point P. But the thing about this one is this tension is inclined, so we need to resolve it into two components. One component will be required, the other component may not be necessary. So if we resolve it into two components like this, horizontal and vertical components, the line will run this way and the other one will run the other way. what we resolved is the t into two components. Now if this is 30 degrees, that means here is the 30 degrees. By alternate angles, this is 30, this is 30. We can as well call here 60 degrees if you like. So we'll be able to find this and find this by resolution. That's mechanics. Okay, this particular, if we're using this 30 degrees here, this particular component will be t cos 30 degrees, while this particular component will be t sine 30 degrees. So this component is t cos 30 degrees, while this component is t sine 30 degrees. And most likely this is the one we will use, because that is the force perpendicular to the flagpole, and not this one, because this one will not produce any moment. The idea is, just like in this question, anytime you're taking moment, it has to be force times perpendicular distance. For instance, the moment for F will be F times the perpendicular distance, which is 10. If we're taking the moment for 100 Newton, it will be 100 times the perpendicular distance, which is 10. If we're taking the moment for 15 Newton, it will be 15 times the perpendicular distance, which is 12. If we're taking the moment for G, for the weight, it will be the value of the weight times the perpendicular distance, which is from here to here. So if you are looking at a horizontal force, you'll be thinking of a vertical distance to be able to have a perpendicular relationship. Force times perpendicular distance. Force times perpendicular distance. Force times perpendicular distance. So 15 Newton times this, because the pivot is P. 15 Newton times this perpendicular distance, 12, will be the moment we use. F, which is this force we're looking for, times the perpendicular distance, which is 10. That's the perpendicular distance to where the pivot is. 10. If we're using 100 Newton, it will be 100 times the perpendicular distance, which is also 10. You know, we discover that this 150 Newton will produce no moment, because it is exactly at the point of the pivot. Also, this 200 Newton will produce no moment, because it has no perpendicular distance in the vertical direction. Okay, so I said all of that to emphasize that this is the moment, this is the force we will eventually consider. T sine 30 degrees, which is the force, and then the perpendicular distance, which is the distance from here to here. The blue force is, the blue component is the one that we will use. The yellow component will produce no moment, or will produce a zero moment. Okay, so that's that about that. Basically, you just apply the conditions for equilibrium. Total forces in one direction equal to total forces in the opposite direction. Total clockwise movement equal to total anti-clockwise movement. Any one of them can be applied first, you know, to be able to get all that we require. And then, of course, remember that the center of gravity is the point where the resultant weight of an object appears to act. That's where the weight will act, like this case, or the one example we solved, where if it is a uniform cross-sectional area, the center of gravity will act at the geometrical center. Okay.